Okay, good afternoon and welcome back to the Nexperia Power Live GaN channel. We're here with you for another 2 hours to discuss a number of design and technology insights, and we'll continue with our discussions now on common application issues with GaN FETs. As before, the session is scheduled for about 25 minutes, so we'll give a brief introduction and then open the floor for questions. So please do join in. You can use the speech bubble in the bottom right of your screen to ask a question. I'm joined again by Jim Honnier and Dilda Chowdhury, both from our GaN FET division. So with that, I will hand back to Jim.
Yeah, hello. This is Jim Honey. I'm Director of Applications for the GaN product line. And we'll be talking about common application issues with GaN FETs and give you some tips for designing with our parts successfully. So the product line at Nexperia includes both leaded and surface mount packages, as you see here, the TO247 and the new copper clip package, our CC pack 12 by 12, available in top side cooled and bottom side cooled versions. Whether you're designing with the leaded or the surface mount parts, there are some details to keep in mind. And that's what we're going to be looking at here in the next few minutes. Designing for stable switching, which means we need to compensate for package inductance, PCB parasitic resonances, damping the gate loop, making appropriate driver selection, and designing for minimum EMI, which tends to go hand in hand. Minimizing the overshoot, the ringing, the oscillation, minimizes the signal sources that can become EMI problems. If you haven't looked at our product lineup, these are the parts we're offering: a 50 milliohm FET in the TO247 in our first generation technology, that's the H1. In the next generation, H2, 35 milliohm, also in a TO247, and then 33 milliohm second generation part in the surface mount package, and as I said, both top side and bottom side cooled versions. Okay, designing for stable switching. Key thing, mind the parasitic inductances. And this is a key point. GaN FETs have gain at frequencies where the parasitic inductances and capacitances on your board can become feedback elements. With slower devices, you might get some ringing due to these resonances, but the transistor didn't have gain at those frequencies, so there was no danger of amplifying the oscillation. With a high-speed transistor, this becomes an issue. There is a real possibility of amplifying ringing in the 100 megahertz range and having a sustained oscillation. So that's a major challenge, and minimizing, avoiding damping these resonances will become a key issue so that they cannot be amplified. That includes PCB inductance, and a key one is resonance on the DC bus. If you look up there in the upper right corner, we've circled the PCB inductance and bypass capacitance. Now, typically, no matter how careful you are with power planes and ground planes, there will be inductance in the DC link. The capacitances themselves have series inductance, and that resonance will act as a load on the transistor when it's in transition between the on state and the off state. And that's a key point here, is that even though these are switching transistors, to get from on to off and off to on, they have to go through a linear state. And if while they're in that transition, there is feedback that allows them to go into sustained oscillation, they very well could. So that's what we want to be careful of. And that DC link resonance can be a load on the transistor. And so damping that is an easy way to eliminate that resonance as a possible source of oscillation. In these figures, we're showing what the inductances are on the board. In the middle one there, we're showing only the external inductance in series with the drain and the source. And these are critical because any transient current in the output loop flows in those inductances. So those are key ones to minimize. On the right-hand figure, you see the internal package inductance as well. Now, you don't have control over those as a customer, but we do. And with surface mount part, we've made those a factor of 10 smaller than they are in the leaded part. And the waveforms are much nicer, lower ringing, lower overshoot. But that's not to say the TO-247 is not usable. It's actually quite usable at typical application frequencies in the hundreds of kilohertz. Right? Keep in mind, we're not making gigahertz RF amplifiers with these GaN FETs. We're making power switches for typical power conversion frequencies. So the TO-247 can be used, but because of the higher internal package inductance, extra care needs to be taken to damp resonances which could become amplified. So here will be our recommendations. These are figures taken from the data sheets. On the left is from the H1, the first generation, and on the right is from the second generation. And if you look there, the figure on the left, right at the DC bus, we're showing RC DCL, the DC link RC snubber, placed as close as possible to the drain pin. We'll recommend 20 nanofarads, 4 ohms. That's convenient to make with 10 nanofarad, 8 ohms in parallel. And that effectively damps the resonance of that DC bus supply. So that's good medicine. It doesn't add to the switching loss. We recommend that in any case. For the first generation, you see there's an RSN CSN, which is a snubber on the switching node. Now this will add to switching loss, and so our data sheet provides recommendations for how much to use, and it depends on your maximum load current. The higher the current, the more important this snubber is for maintaining stability. But by the same token, the higher the current is, the less impact the switching loss has on total efficiency. So it's not a big factor, but it's one to be careful that you don't use more than is necessary. For the second generation, we actually do not recommend a switching node snubber. That's not required at all for the second generation. One note you'll see there, for the H1 first generation, there is an internal gate ferrite bead, whereas in the second generation, an external gate ferrite bead is required. It is a requirement in either case. It's just with the first generation, we integrated it, and with the second generation, we leave it external. That is critical for damping the gate loop, the gate drive loop. And the signal noise source, which is the biggest problem, is the source inductance, right? That's common to both the input and the output loop. And so at turn on or turn off, when there's a DIDT on the source inductance, that ringing is hard to avoid, but the thing we don't want to do is amplify it, right? And so if we decouple that ringing from the gate drive loop, we avoid amplifying the ringing, which can lead to instability. So that's the purpose of the ferrite bead. In the surface mount package, where that source inductance is so much lower, the required ferrite bead is also much lower. A much smaller value is recommended. And again, you can check the data sheet for what our recommendation is there. The final element, the gate resistance, that slows down the turn on, the DIDT. And so the excitation of the resonances can be reduced by using a lower value gate current, which is what RG is for. The data sheets will give a recommendation, some 10 to 30 ohms, depending on which device. The driver itself will switch 0 to 10 volts, 0 to 12 volts. The parts have a 4-volt threshold, so a negative gate drive really isn't required. It is important to have a common mode transient immunity. 50 to 100 volt per nanosecond is appropriate. You have some control over DVDT with the gate resistor. So that's why we specify a range, but that is a key parameter for the gate driver. Okay, minimizing EMI, and again, thinking of a hard switching half bridge. Key point here, the I in EMI stands for interference. For there to be interference, you need three things: a transmitter, a receiver, and a coupling mechanism. So high dB/dt by itself does not create an EMI problem. Eliminating the coupling is the key. Now, obviously, that's not completely possible, but to the extent you can minimize it, you can keep high dB/dt from being an EMI problem. For conducted emissions, one of the elements that is responsible is capacitance of the primary inductor. So here we're showing a 4 kilowatt totem pole PFC, where the PFC inductor is the large toroid. And as you can imagine, it's hard to wind a toroid that large without some capacitance. But the dB/dt at the switching node will go right through that capacitance into the grid. And if we can do something to minimize the signal that's seen by that capacitance, we can minimize the coupling. Well, this smaller toroid with just 10 or 11 turns on it does that by putting that in series with the larger inductor. That small capacitance is in series with the larger capacitance and effectively minimizes how much signal is transmitted through to the power grid. So if not that method, then some method of low capacitance winding on the power inductor is very beneficial. For radiated emissions, key thing to minimize is the area on the switching node. So that's this figure over to the right, where we've identified the switching node in the circuit. Any copper on that switching node which has capacitance to the surroundings is potentially a signal source for radiated emissions. So minimizing that is a critical factor. Okay, and final point, just sample layouts. On the left, TO247 half bridge, where we have two TO247s side by side against a heat sink. You can see the high side transistor on the left, and its drain is the leftmost pin. The low side is on the right, and the center pin is the source. And then the switching node is that node in the middle. And this is a layout that works well. We're not showing the power and ground planes that provide the DC link. And in this case, you can see RC snubbers across source and drain of both the high side and the low side, which is providing maximum stability at highest power. Okay, on the right, an example layout for the CC pack. And here you can see the high side device on the left, the low side on the right, and the closest spacing that we can achieve for the switching node, so that we have a small amount of copper and very low inductance between the two transistors. So these are layouts that have worked well for us in our circuit boards. Okay, with that, conclude my comments, and we'll open it up for any questions and insights that you all have.
Super, thank you very much, Jim. Okay, just to remind everyone, if you would like to answer a question, you can do so by using the speech bubble in the bottom right of your screen. We have already had a number of questions in, so let's make a start. Jim, what is the difference between switching transistors and transistors which are optimized for linear operation by means of construction and parameters?
In terms of construction, a transistor that's designed for linear operation will typically be more spread out, right? It's intended to operate in a mode where there's continuous dissipation and heat generation. And so you'll make a larger die for a given current handling capability, keeping in mind that you will be dissipating power continuously. I think a bigger factor is simply characterization. A transistor that's intended to be used in a linear mode will be characterized for use in that mode. So factors that are important, like transconductance, would be controlled, characterized, specified on the data sheet. And so that's, if you try to design with a switching transistor in a linear circuit, that will be a problem, as a lot of the parameters that you're interested in simply are not measured, specified, or controlled.
Okay.
Yeah.
Thank you, Jim. Next question. What is the impact of very low loop inductance to efficiency?
The main impact, I would say, is in creating instability. Now, there's an assumption here that we're talking about converters in the hundreds of kilohertz range, and the nanohenries of loop inductance are not typically slowing the device down so much that you're seeing a big increase in switching loss because of slowing down the transitions. It's more that they create the possibility for instability, and to damp those resonances associated with the inductance, you need things like RC snubbers or lower gate currents to soften the turn on a little bit. So the measures that you take to keep the circuit stable are what lower the efficiency more than the inductance themselves actually slowing down the device. That's especially true with the cascode configuration, where the turn-on mechanism involves the silicon MOSFET, the low-voltage silicon MOSFET, turning on the GaN FET with an internal current loop. And so that external inductance really doesn't play the role in turn-on that it would with a single-chip FET. And so for our devices, the source inductance, for example, I would identify as a bigger problem in terms of creating instability than simply slowing down the turn on and directly creating loss. It creates loss indirectly because we have to make sure that we've appropriately damped and stabilized the circuit because of that.
Okay, thank you, Jim. And next question, does the Nexperia GaN FET have a low inductance Kelvin connection to the gate?
The TO247 does not. It's a traditional 3-pin TO247, and for the reason that I just mentioned, because the cascode turns on with you could think of a 2-stage turn on where the silicon FET turns on, and when it does, it turns on the GaN FET. What that really means is this initial surge of current is an internal current loop, not flowing in the source inductance, and therefore the source inductance doesn't play the role that you might think that it would in a single chip FET. So in development, when we have made 4-terminal TO247 devices, we didn't see a real benefit, and that's why the product that we offer is a simple 3-terminal. The CC pack, let me just, I'll go backwards here to where we show the package. You can see it's a 12-lead package, 5 source pins and 1 gate pin on the low voltage end of that package. That first source pin, the one right next to the gate, actually could be used as a Kelvin source. The way the copper clip leads work, there's very little common inductance between the 5 pins. They all go pretty much directly to the source with very low inductance. So you could use that first source pin as a Kelvin contact. I personally wouldn't recommend it because you're losing 1/5 of your current carrying capability for the primary switched current, and I think that's more detrimental than any improvement of the switching, but it could be used that way. I mean, there is a pin that could be used pretty effectively as a Kelvin source. Again, not a recommendation, but a possibility.
Okay, thank you, Jim. It's also probably a good time to mention that actually the next live discussion after this one is taking a further look at CCPAC as well. Next question is for GaN. Is there any EMC implications for multi-layered PCB boards?
Yeah, I would say the implications for EMC are the typical implications of any circuit, right? Having a multi-layer board gives you the ability to have ground planes and power planes, which are great for minimizing loop inductances. It does mean something you need to think about is which layer you're routing traces on, and that you are in fact increasing loop areas if you drop down to the opposite side of a board and back up. Like I was saying, these small inductances that at lower or with slower devices are not critical. With fast devices, they do become significant. So a multi-layer board does give you the ability to create loop area simply by dropping down to lower layers. In general, though, I wouldn't say there are very specific issues related to multi-layer boards. Unless I don't know, Dilder, defer to my colleague Dilder Chowdhury. Can you think of anything I've missed there?
Yeah, no, I think obviously multi-layer board also helps sometimes at mutual inductance cancellation. You can have your current flow paths, you can carefully pick so that it doesn't, it doesn't make the EMC or EMI any worse.
Yeah, very good.
Good, thank you very much. And we've probably got time just to squeeze in one last quick question. Since the ferrite bead increases impedance in the gate drive, isn't that bad?
It seems like it would be if you think in terms of trying to keep a very low impedance gate drive. The thing to keep in mind with the ferrite bead is its real impedance at a very high frequency, right? So at 100 megahertz, it looks like real resistance. At lower frequencies, it's just a short circuit. So it's not like an inductance, which is an inductance at all frequencies. It's really giving us real impedance at the high frequency where the ringing occurs. So it is beneficial in damping resonances. It's not detrimental in the sense of adding impedance when you don't want it. So it pretty much does what you want and doesn't do what you don't want.
Okay, good stuff. Thank you very much, Jim. So that's all the time we have for questions in this session. We're going to take a short 5-minute break, but we will be back with you shortly with our next discussion, which is taking a look at our new copper clip surface mount package technology for gallium nitride CCPAC. So in the meantime, take a look at the links below this video screen. You'll see more information on the topic that we've just discussed, and we will see you back here shortly.